All right, part two. So again, how much heat is required to vaporize 2 moles of water at 298 degree Kelvin? Heat of vaporization or enthalpy of vaporization for water is 41 kilojoules per mole, and the molar heat capacity of water is 75.4 joules per mole Kelvin. Okay, so again, the first step that we're going to take is to find the heat required to bring the water to 100 degrees Celsius, which is the boiling point of water. Okay, now here we're given things in Kelvin, but it's really easy to convert from between Kelvin and Celsius. Okay, so our final temperature, the boiling point of water, is going to be 373 Kelvin minus our 298 degree Kelvin. So that's going to be a change of 75 degrees Kelvin. Okay, so that's how much temperature change needs to occur for every mole of Kelvin as well. So again, molar heat capacity is going to be what we are using to determine how much energy it takes to make that change occur. So we're going to multiply our 2 moles of water by the molar heat capacity of water by our change in degrees Kelvin, which is the same as the change degrees Celsius. Okay, so 2 moles times 75.4 times 75 is going to be about 11,000 joules. 11,000, that's a pretty big number, so we can go ahead and convert that to kilojoules. So that would just be dividing by 1,000 or moving the decimal places 3 places to the left. So again, 1, 2, 3, so that would be 11 kilojoules, same thing. Okay, so that is making our room temperature, essentially water, into the boiling, bringing it to the temperature that it needs to boil so that the phase change can actually occur. So that is the first part of the graph, that vertical line up, that temperature change. Next, we're going to talk about the plateauing phase, the actual energy it will take to make all that water boil. So step 2, add the heat of vaporization for water. Heat of vapor, or the enthalpy of vaporization, is going to be 41 kilojoules for every mole. So all that we have to do is multiply our 41 by the 2 moles of water that we have to figure out how many kilojoules that will be to boil all of that water, or vaporize all that water. Okay, so 2 times 41, and then here's the 11 kilojoules we got from before, and that's going to give us 93 kilojoules per mole. I think with the aluminum, I forget if I already added it or not, but if there was confusion there, that could be why. So this 2 times 41 is step 2. This 11 kilojoules came from step 1. Okay. Sublimation is another phase change that occurs. It's where solids immediately evaporate without going through the liquid phase. So one really common example is with solid CO2, dry ice. It goes immediately from a solid to a gas. So that's sublimation. As intermolecular forces are stronger in solids, the vapor pressure of solids are usually pretty low because you don't usually have a lot of the solid going straight into a vapor phase, which is what vapor pressure is. Solids with a high vapor pressure have weak intermolecular forces. So remember, there's an inverse relationship between intermolecular forces and vapor pressure. So really weak means that a lot of particles can escape, which increases the pressure of that vapor, essentially. Okay. So if you've ever had mothballs as well, or have smelled mothballs, I live in a really old house, so we usually keep some in our closets because we get a lot of bugs and things that can eat your clothes and stuff. But mothballs, if you've ever encountered them, have a very strong smell, and that's because they have a very high, fairly high vapor pressure, considering it's a solid. So that's why you can smell mothballs so much. And again, dry ice is another common example of that. So the energy required to sublimate 1 mole of a solid is equal to the energy required to liquefy and then vaporize 1 mole of that substance. So essentially the heat of vapor, or the enthalpy of vaporization, which would be, or excuse me, the enthalpy of sublimation, which would be delta H sub, would be equal to the enthalpy of fusion plus the enthalpy of vaporization for that substance. So for ionic compounds, they typically have really low vapor pressures, again, because they have strong Coulombic interactions between cations and anions. So you can kind of think of it like strong intermolecular forces. So again, a strong intermolecular force would mean a relatively low vapor pressure. So since ionic bonds are very strong, ionic compounds have very low vapor pressures. You don't have many particles escaping into the vapor phase. So again, this is your enthalpy of sublimation, delta H sub, sublimation and deposition of water at 0 degrees Celsius and 1 atmosphere. So deposition would be the exact opposite of sublimation. So sublimation, we have solid going to gas. It would take 47 kilojoules per mole, and deposition would be gas to liquid. It'd be negative 47 kilojoules per mole. Where did we get 47? If you remember back, we had 41 kilojoules per mole for the heat of vaporization of water, and 6 kilojoules per mole for the heat of fusion for water. So again, the sum of those two things equal our enthalpy of sublimation. So again, here's the enthalpy of vaporization, 41 kilojoules per mole. Heat of fusion, 6 kilojoules per mole. If we add those together, we get our enthalpy of sublimation, 47 kilojoules per mole. So this is true at constant temperature and pressure. Increased pressure is going to basically determine our kind of like our boiling point. So again, if you boil a pot of water on a mountain, it takes a different amount of time than boiling the same pot of water at sea level, and that's because boiling occurs when the atmospheric pressure and vapor pressures are equal. So if we decrease that, we can boil a lot faster. If we increase it, it takes a lot longer in order for that boiling to occur. Okay, so that sums up section 6.5 notes. We do have a 6.5 worksheet. On Friday, if you were in class, I did give you a packet for units, the rest of unit 6, 7, and 8. So if you weren't here, that's fine. I can upload PDF files onto Classroom, no problem. I'm not sure though if the one I gave on Friday includes the 6.5 worksheet. For some reason, I think that got left out. So I will definitely upload that to Classroom. You'll be able to find it under classwork right at top under COVID-19. So if you work on that, the worksheet itself will be due on Monday. So remember, we don't really have class on Friday. Tomorrow is Thursday. We will be doing a Google Meets, which will be my first time, so bear with me with that. But we will go over questions. Tonight, I'm also going to give you a Google form for you to basically select problems for us to go over during our Google Meets time. So it'll just be a Google form. Fill it out before 5 p.m. so I can kind of be ready for those and have everything ready so that we can use the most of the half hour that we have. And if we don't get to doing everything live, I can always record myself doing those solutions and going through those problems as well. We'll also talk about doing a potential since we can't do office hours at school anymore due to everything that has been changing, I'll do like a voluntary office hour session on Friday so we can determine a time tomorrow during the meets that would kind of work for everyone. Yeah, okay. Let me know if you have any questions. It's been real.